in different coordinate systems. For rectangular coordinates, we take the derivative with respect to x, and that's our I component, the derivative with respect to y, and that's our j component, and the derivative with respect to z, and that's our k component. We're also going to do some things in cylindrical polar coordinates, right? Which is some radius r, some angle theta, and some altitude z. So we will do some cylindrical polar examples and also spherical polar examples. When you think of rows of spheres, and at some point we have a radius r, an angle from the z-axis, which is phi, and an angle of the projection onto the xy plane, which is our theta. Now, this is where I said it's going to get complicated and then it's going to get simple again. And the reason for that is the examples that we're going to be doing, and even the examples that you would encounter in a somewhat higher level physics, these guys are going to go to 0 from symmetry. So even with these frighteningly named cylindrical polar coordinates and spherical polar coordinates, the thing that we're going to be most concerned with is just the radial component there, and the others are going to go to 0. The situation here is we can usually rotate our coordinates so that one or more of these guys can go to 0 as well. But none of that is really too important. It doesn't change things very much, except it changes the variables that we're taking the derivatives with respect to. For those of you who are unfamiliar with partial derivatives, the process of doing it is really much simpler than the explanation. So I'll just do a quick example here. We have some function in x, y, and z. Let's say 3xy squared 2xz cubed 2x squared y. So what you do is you treat every other constant except the one you're differentiating with respect to as if it is a constant. So if we are going to find the partial f with respect to x, we treat y and z the same way we would treat this 3, and we treat it as a constant. So our first term is going to just be 3y squared, comes through unaffected. X to the first, the derivative of x to the first with respect to x is just 1. So our first term becomes 3y squared. Similarly, we take the derivative of 2xz cubed with respect to x, and our x, again, the derivative of x with respect to x is 1. The rate that x changes as x changes is the rate x changes. So that leaves us with a 2z cubed here, because we're treating those as constants. Lastly, derivative 2x squared y with respect to x. So that's going to be 4xy. And we could do a similar sort of thing if we want the derivative of f with respect to y. Then in our first term, we treat the x as a constant. So we would have 3x y squared. So we would bring down the 2, subtract 1. That would give us 6x y to the first. Our second term has no y in it, so the derivative of a constant is 0. So that one would go to 0. And then our third term, we have 2x squared y to the first. Derivative of y to the first is 1. And that's our derivative with respect to y. And by an identical set of arguments here, partial f partial z, no z's appear in the first term. Its derivative is going to be 0. The second term has the 2xz to the cubed. So the 2x unchanged. The 3 comes out in front. 2 times 3 is 6. X z squared. And there is no z in this last term, so it would drop out as well. And those would be our 3 derivatives. So, using the gradient operator on a function produces a vector that points in the direction of the maximum rate of change. That's why we call it a directional derivative. The gradient of potential energy is force, and the gradient of potential is field. So I've been previewing this idea all along. The relationship between potential energy and force is analogous to the relationship between potential and field. As I said, the examples we use in this course reduce to fairly direct calculations. They simplify a lot. A lot of terms that we use go to 0.